Hello students, welcome to the course on hydraulics FMH 202, and today we are going to start with a new chapter, that is hydraulics turbine. Now you must be aware what is hydropower plant, right? From where we produce hydropower energy. So in Bhutan we have plenty of hydropower plants, and if I give you an example, Tala hydropower plant, Chuka hydropower plant, Mangdechu hydropower plant, Dagachu hydropower, these are all hydropower plants. We harness the potential energy of water, uh, and convert it into electric energy with the help of a turbine. So that is what we are going to study today. So basically, if I just give you an overview of what a hydropower plant looks, and let's start with the first thing, that is the reservoir. Reservoir is a small or a large. In our case, is a small uh, dam. A small reservoir means pounding of water because there is a construction of a dam. So dam is an hydraulic structure that is built across a river. That behind the dam we have the reservoir. From that reservoir, a small channel is taken out as intake channel, and then here there's a small tank which is also known as the desilting chamber or desilting tank. All the sediments which are carried by the water is led to settle here, and from this a channel is constructed. I mean, in Bhutan most of these parts are not in open space. These are constructed in interior of a mountain. So these are everything is interior of a mountain, so it is in the form of a tunnels. Okay, even the tank is inside the mountain, so you'll not be able to see this, but understand that there is a tank there. So this channel, which from the desilting chamber to the powerhouse, the channel that carries water is the headdress tunnel, or we call it headdress only. In case of Bhutan, we call it tunnel because it's a tunnel. Then there's a four bay. In our case, we don't have a four bay for most of the hydropower. Instead, we have a surge tank. It's just for now, just understand it's a temporary storage of water. It has different functions, which we are going to discuss later. Okay, so from there, and it comes to the powerhouse. This is where it will house the turbine and the water. Because if I give you an example of a impulse turbine, the water is converted, the pressure energy is converted to kinetic energy with the help of a nozzle. The water then strikes the turbine rotates, which makes the shaft rotate, and then the electric power is generated. Okay, and whole the scheme, okay, this entire scheme is known as hydropower plant. So run-of-river hydroelectric projects are hydropower generation plant whereby water is not stored or may have little storage for a limited amount of time. All the hydropower plants in Bhutan are of this type. So in Bhutanese context, the hydropower plants are of run-of-river, meaning we are not storing water for a very long duration. We are simply storing it for temporary purpose, and then we are taking out the water for generation of hydroelectric power. And here is a schematic. Okay, now let's understand what is a catchment. Catchment area of a river means all the places, okay, for where the water gets contributed to the same point. So that is the catchment. And somewhere in the outlet, dam is constructed. Because there is a dam construction, a reservoir is formed. From the reservoir there is a channel or a tunnel is constructed to the powerhouse, where in powerhouse a turbine is there, and this turbine is made to rotate because of the fluid energy here, and then finally electric power is generated. So that is an overview of hydropower plant. Further, let's understand what is turbines. Now turbines are the machines which converts fluid energy to the mechanical energy, and then the mechanical energy is converted to electrical energy. Okay, so turbine in a very simple term is a device that extracts energy from the fluid, converts the energy held by the fluid to mechanical energy. Okay, now if a machine adds energy to the fluid, then that would be known as pumps. And pumps and turbines work in opposite way. So turbine harnesses the energy of the fluid, pumps adds energy to the fluid. Okay, moving on, the classifications of turbine. So here we have the classification of turbine. Turbine may be classified based on the head and the quantity of water available at the inlet, or the type of energy at the inlet, direction of flow of water in the runner. Okay, runner here means turbine. Typically is a turbine only, means with something that is moving because of the fluid. There is there when there is interaction between fluid and the machine, which is making the fluid is making the machine to run. So that's why it's known as runner here, but generally it is a turbine. So according to the name of inventor, so in our course we'll be basically referring to a turbine by a name. So there are three types. For now, we will be studying three types of turbine. This is Pelton turbine, invented by Alan Pelton, Francis by James Francis, and Kaplan by Victor Kaplan. So most of the time, I'll be referring turbines with their name. Okay, and also it is classified based on specific speed. Now, what is specific speed? We're going to study in detail, and let's move forward. Now, based on the quantity and the head of water available. So, based on the head available, the turbines can be of low head that operates with less than 45 meters of head, medium head within 45 to 250 meters of head, and high head which operates with more than 200 meter head available at inlet. So, in Bhutan, most of there are hydropower turbines are high head turbines, and based on the hydraulic action of water. Now, typically, you may have assumed a turbine to be, when water, like I explained in the previous slide, water, the pressure is converted into the kinetic energy with help of a nozzle, then the jet strikes the turbine, which makes it run. So that is true for Pelton turbine. But there are other types of turbine which does not use this principle. Instead, they work on the pressure difference between inlet and outlet of the runner. When there is a pressure difference, then water tries to gush out from high pressure to low pressure. Because of this, there is a reaction force is generated on the runner, which makes the runner run, making the turbine run. So because of, the action is different. Actually, hydraulic action of water to the machine is different. So there are two types: impulse and reaction. Pelton is an example of impulse. Kaplan is an example of reaction. Kaplan and Francis, in fact. Now, let's understand this impulse turbine. Like I explained, there is a nozzle, right? Water is in the form of jet strikes the vane or the cup plates. This, because of this action, it makes it to rotate. The turbine is then rotate. So see, you can see here the runner. Instead of using the term turbine, then they're using the term runner, because the runner applies to all the turbines. Basically, water is making it run. That's it. Now, if we take one particular vein or the cup, it looks something like this. Okay, and if you and what happens is jet strikes this portion in this region, okay, and it gets splitted into two halves, and water goes out from this region. You can see this arrow, right? So see, water strikes, the jet strikes somewhere in between. This gets, because of this a divide here, the water gets divided and water gets out of this region. So that is for impulse turbine or the Pelton wheel. And Kaplan, there's a reaction turbine, there's a Kaplan turbine. Okay, so see, the action is entirely different. Water is accompanying actually to the runner. It moves out. When it moves out, there's a pressure, there's a huge pressure here, and there's less pressure in this domain. Okay, in this region there's pressure is less, here there's lots of pressure. So when water tries to move from high pressure to low pressure, it applies a force, see, reaction force. Because of this force, it makes this rotate. So that is the action in the reaction turbine. Okay, that's the action of water in the reaction turbine. So this is the two types of impulse and reaction turbine. Further, so see, I have given you all the images. Okay, so this is the particular the Pelton wheel. There's a jet which strikes here, it makes this rotate. Francis and Kaplan, usually they are they're not open, okay, they come in casing. This is the casing, and this portion of the casing is known as draft tube. We'll learn more about what is draft tube and what is function later on, but right now just understand that Kaplan and Francis have to be inside some kind of casing, because the major work is done not by the jet, but in fact it is because of the pressure. So that's why it comes within the casing. And there's a difference between hydraulic action impulse turbine and the reaction turbine. Most importantly, you can read this conversion of fluid energy, how the fluid energy basically is talking about the interaction of fluid and the runner. So available fluid energy is converted into kinetic energy by nozzle. Like I said, here the energy of the fluid is partially converted into kinetic energy before the fluid enters the runner. Okay, so that's the major difference, and there are many others which I would like you to read through. It is self-explanatory, and when you read it, you'll understand it. Based on the direction of flow of water in the runner. So you can see this is tangential. The jet is striking the vane tangentially to the runner, right? So this is tangential type. Now, Francis is a typical type of a mixed flow. It is coming radially, but it's going axially. So that's why it is a mixed type flow. Kaplan is an axial flow, meaning it is coming in the direction of axial, and it's this axis, okay, the axis of rotation. So it comes in this direction and leaves in this direction. So there's a pure case of axial. Ima Pelton is a tangential, and Francis is a mixed flow type turbine. And that's what I have just explained here: tangential flow, radial flow, axial, and mixed flow. Well, radial is no more of use these days, okay? So we have tangential, Pelton, axial, Kaplan, mixed flow, the Francis turbine. So based on the specific speed of a turbine, now there's a different classification. So let's define what is specific speed. Specific speed of a turbine is defined as the speed of a geometrically similar turbine which produces unit power when working under unit head. So that is the definition of a specific speed. So here one thing comes, geometrically similar turbine. We have studied about geometrically similar, kinematically similar, dynamically similar, right, in the chapter dimensional analysis. So the concept has to be applied here. So it says that specific speed is this geometrically similar turbine which produces unit power working on a unit head. So the speed of that turbine is known as the specific speed. And here the few data is given. Pelton turbine has 8 to 30, Francis has between 50 to 250, and Kaplan, the specific speed of Kaplan lies between 250 to 850 RPM. Okay, speed means revolution per minute, so the unit is RPM. Based on the orientation of the runner, so you can see here the Pelton wheel, this orientation, the shaft is the horizontal direction, right? It could be vertical direction also. Now, in the advantage of keeping it vertical would be, instead of one jet, then you can use multiple jets. So right now, this is the orientation of the shaft is horizontal. So there is only one jet possible. For Francis and Kaplan, as you can see, it is a vertical, right? The shaft is vertical. The vertical. So based on the orientation of shaft, also we can classify the turbine. Now, like I said, specific speed, once again, it is coming, but we have to discuss in detail, okay, what is specific speed. For now, just understand that it is the geometrically similar turbine that would develop one unit power and working on unit head. So the advantage is it irrespective of sizes, okay, the size factor is removed when you use the term specific speed. So your turbine could be a smaller or a larger, but it should have a similar specific speed because of the fact that when working under one unit head, the speed that is working under producing one unit power working under unit head. So that is, and by formulation it is given by this expression, but in future we will derive this expression. Right now just understand this. Right now you just have to understand what specific speed means. Later on we'll discuss in detail. And let's talk about the losses and efficiencies in hydraulic turbine. Now, this is a particular setup of a impulse turbine. See, there's a reservoir, there's a surge tank. In the previous slide, I have shown you the 4-bay, but here I have shown you the surge tank. Basically, functions the same way. Okay, right now just understand there's some tank, surge tank, which will temporarily store water, and water when it then the water comes from the headrest tunnel, then comes into the powerhouse, and to regulate the flow there is a spear in a Pelton wheel. Okay, this is true for Pelton wheel. So there is a spear. So this spear, we can adjust the spear depending upon how much water is required. And if we need to stop this wheel, then there's some, we can regulate this flow, which will strike in opposite direction, and then it will eventually come into hold. So this is a complete setup of a Pelton wheel. And the total head between the reservoir and the runner is known as the gross head, that is without reducing any frictional losses. But the net head is after reducing the frictional losses. When water comes from this region to this region, obviously some energy is lost due to friction, right? So that is the actual net head available at the runner is known as the net head. All right, and let's also discuss about the losses, from where there can be losses. Head loss in the penstock is basically because of the frictional losses. Head loss in the nozzle. Now we know that when pressure is converted into kinetic energy, that not there is something nozzle, right? When water flows through nozzle, then there is some losses. And hydraulic losses, when it strikes the blade, there is some friction here, and it may not strikes. When it strikes, there could be some shock, and there could be some losses. So these are the hydraulic losses. For the leakage loss, now in our previous slide, when water strikes this vein, there could be some portion of water which may not strike, so we can call this as a leakage losses. Okay, now mechanical losses comes when this runner is running and it has to run the shaft. When it runs, then there's some bearings and many other movable parts are there, and whenever there is a movable parts, obviously there is friction and energy is wasted in terms of heat energy as a heat energy. So there is a mechanical losses. And generator losses means now mechanical power has to convert it to electrical power, and because through with the help of a generator, and there could be some losses in the generator. So this is the generator losses. Now to get an overall picture of it, so let's understand this color coding. I have shown the color coding in terms of energy available. So there's a maximum energy is available at the reservoir, but as it moved through all the network to the turbine, the energy is lost because of all these factors. So I have all listed all the factors here. Most important, this is a typical case of a reaction turbine. Okay, similar diagram can be plotted for impulse turbine, since you already have a maximum idea of what impulse would look like. So I thought of it would be interesting to put reaction turbine here. And with the losses comes the efficiency. So there are 4 types of efficiency: hydraulic efficiency, mechanical efficiency, volumetric efficiency, and overall efficiency. Let's discuss this. Now, hydraulic efficiency is given by runner output divided by actual power supplied to the runner. Now, in this previous slide, I have discussed about hydraulic losses, right? So, if hydraulic efficiency is 90%, right, which means there is 10% losses. That 10% losses is accountable for this hydraulic losses. So, if hydraulic losses is more, then hydraulic efficiency will reduce. So, this gives a better understanding for engineer to design as of which part is where the energy is lost, so we can work on it. Likewise, volumetric efficiency is all the volume of water that is which is in a jet may not strike the turbine. So because of there could be a small fraction of water which is not actually striking the runner. So because of this, there is a uh, losses. So to account for that, we have volumetric efficiency. And similarly, mechanical efficiency is due to mechanical losses. Now it accounts for the mechanical losses given by shaft power divided by runner power. Now runner is the Pelton wheel, or the movable part which comes in interaction with the water. Shaft is the this, when the runner runs, it makes the shaft run, and these two are coupled with some kind of other machines, bearings and so many other stuff. So whenever it runs, there is obviously frictional losses and so many other stuff going on, so there will be some losses. And the overall efficiency is, it is the mechanical efficiency time hydraulic efficiency times volumetric efficiency. So these are just the mechanical efficiency, hydraulic efficiency, and volumetric efficiency. If you multiply all, you get the overall efficiency. And the operation of a turbine, let's discuss where would be each type of turbine be best suited to work. So the Pelton wheel is, it is a high head turbine, meaning it operates when the head is high but the discharge is low. So in this region, the Pelton wheel operates. The Francis turbine works in a medium head to medium, high discharge. If the discharge is high but the head is medium, then the suitable turbine would be Francis turbine. And if the head is low and discharge is very high, then the suitable turbine would be the Kaplan turbine. And why do I say this? Is because of these reasons. Okay, because of the efficiency factor. If we want more efficiency, then we may have to use in the particular region. If we use the other way around, then we may not achieve the efficiency. Like you can see from this chart, the efficiency, maximum efficiency range is maximum. If you really compare three turbines, then we have the Francis turbine is slightly leading over other two turbines when it comes to the specific speed and the efficiency. So usually Pelton wheel operates on a very small specific speed, and Francis turbines has a large region where it can operate, and then Kaplan turbine also has a quite a large region where it can operate. And this point shows the maximum efficiency for particular specific speed. So to achieve this in real world, it would be very difficult. It has to be tested experimentally number of times. So with this, I would like to end the lecture right now and continue in our next video. Thank you.